Fine. Let's start. Number 10. The wall of light. Point a telescope at any patch of sky. Any patch at all. Up, down, left, right. The dark space between two stars. Keep looking. Keep zooming. Keep gathering light from farther and farther away. And eventually, in every single direction, you hit the same thing. A wall. Not a wall of brick or stone. A wall of light. A faint, even glow that sits at the very back of everything, surrounding us in a perfect sphere, like we're standing in the middle of an enormous, luminous shell. We call it the cosmic microwave background, and it is the oldest thing any instrument has ever seen. Here's what it actually is. For the first few 100,000 years after the Big Bang, the universe was too hot to be transparent. It was a fog, a dense, glowing plasma of loose particles, and light couldn't travel in a straight line through it any more than you can see across a room full of smoke. Photons would move a tiny distance, smack into a free electron, scatter, and start again. The whole cosmos was opaque. Then, about 380,000 years in, the universe cooled to roughly 3,000 Kelvin. And at that temperature, something quiet and enormous happened. The loose particles finally calmed down enough to lock together into the first neutral atoms. The fog lifted. All at once, across the entire universe, light was suddenly free to fly in a straight line. And it has been flying ever since. That released light has been traveling for 13.8 billion years to reach us. It started out as a fierce 3,000-degree glow, but the expansion of the universe has stretched it, cooled it, dragged its wavelength out until today it arrives as a whisper. Just 2.7 degrees above absolute zero. Microwaves. The faint hiss at the edge of the sky. And this is the part that gets under my skin. That wall is the farthest we can ever see with light. Not the farthest we've looked so far. The farthest we can see. Full stop. Because there is nothing visible behind it. Before that moment, the universe was opaque. There are no older photons to catch. We are looking at the surface of the fog, from the inside. So the edge of everything, the actual boundary of the visible cosmos, is not a place. It's a moment. It's the instant the universe became see-through, frozen into a sphere around us, glowing faintly in every direction we turn. And the wall isn't a barrier you could ever fly up to and touch. It's not out there waiting in space. It's the past, rendered as a horizon. To see beyond it, light is useless. You'd need something that can pass through fog untouched. Neutrinos, maybe, or ripples in space-time itself. Things we are only just learning to detect. For now, though, we live inside a glowing shell made of the universe's first clear morning. And every theory we're about to talk about is an attempt to answer one simple, impossible question. What is on the other side of that wall? Number 9. The observable universe is only a bubble. Let's clear up something that trips almost everyone, because it changes how you picture the rest of this video. When scientists say the observable universe, people tend to hear the universe. The whole thing. Everything that exists. But that's not what it means. Not even close. The observable universe is just the part we can currently see. It's the bubble of space, close enough that its light has had time to reach us in the 13.8 billion years the universe has existed. That bubble is big, about 93 billion light years across, once you account for how much space has stretched while the light was in transit. But the part we can see and the part that exists are two completely different things, and the gap between them might be unimaginable. Think about standing on a ship in the middle of the ocean at night. You can see maybe a few miles in every direction before the world fades into dark. That circle around you isn't the edge of the ocean. It's the edge of your eyesight. The ocean keeps going. You just can't see it yet. That's us. That's our whole situation. The edge of the observable universe is not the edge of the universe. It's the edge of how far light has gotten. And every year that boundary creeps outward a little, as light from slightly farther away finally arrives, like the horizon widening as the sun comes up. So how big is the actual thing? We don't know. But we can put a floor under it. Here's how. We measure the curvature of space. If the universe were small and curved, like the surface of a ball, we'd be able to detect that curve, the way you can measure the curve of the Earth if you're careful. But every measurement we make, from the Planck satellite and others, says the universe is flat. Almost perfectly flat. Flat to within about 1/3%. Now, a small curved universe would show an obvious curve. A flat measurement means that if there is a curve, it's so gentle that the universe has to be gigantic for the bend to be that subtle. In 2011, cosmologists Mihran Vardanyan, Roberto Trotta, and Joseph Silk ran the numbers and concluded the whole universe must be at least 250 times bigger than the part we can see. And that's a floor. A conservative minimum. The honest answer might be that it's infinite. Genuinely, endlessly infinite. Going on forever in every direction with no edge at all. Sit with that for a second. The most distant galaxy we have ever photographed, this faint smudge of red light at the limit of the James Webb Telescope, is not near the edge of anything. It's a few inches from our face in cosmic terms. Beyond it is more, and beyond that, more. And we have no evidence it ever stops. Which means the phrase, "what's past the edge of the universe," has a strange answer hiding inside it. There might not be an edge. There might just be more universe. Forever. Most of it permanently out of sight. Not because it's hidden, but because its light is still on the way and always will be. The edge isn't a wall. It's a deadline. And the universe was never obligated to end where our vision does. Number 8. Is the entire universe spinning? Almost everything in space spins. The Earth spins. The moon orbits. The sun rotates. The whole Milky Way turns like a slow pinwheel, taking about 230 million years for one lap. Spin is everywhere, at every scale you look. So here's a fair question that sounds childish until you really chew on it. Does the universe spin? All of it, as one thing. In 1949, one of the smartest people who ever lived decided to find out. Kurt Gödel, the logician, the man who basically broke mathematics by proving there are true statements that can never be proven, was good friends with Albert Einstein. They used to walk home together at Princeton. And for Einstein's 70th birthday, Gödel gave him a present unlike anything else. He gave him a universe. Specifically, Gödel found an exact solution to Einstein's equations of general relativity that describes a universe that rotates. Not the stuff inside it spinning. The entire fabric of space-time, turning. It was mathematically airtight. It obeyed every rule. It was a universe Einstein's own theory said was completely allowed to exist. And it was deeply strange. In Gödel's rotating universe, the spin drags space-time around with it so violently that you get something called closed time-like curves. In plain language, paths through space that loop back into the past. In a Gödel universe, you could in principle travel in what feels like a straight line forever, forward in time, and arrive at your own yesterday. Time travel, not as a loophole, but as a basic feature of the geometry. Einstein, to his credit, was rattled by it. He admitted the possibility had bothered him when he first built the theory, and here was his friend handing him a clean example of a cosmos, where cause and effect could eat their own tail. Now, for decades, this was treated as a beautiful curiosity, a toy, because our universe doesn't look like it's spinning. If it were, we'd expect to see certain patterns, a preferred direction, a swirl in the large-scale structure, and broadly we don't. But here's the thing. The idea refuses to die. Because cosmology right now has a genuine crisis called the Hubble tension. When we measure how fast the universe is expanding using nearby objects, we get one number. When we measure it using the ancient light of that wall we talked about, the cosmic microwave background, we get a different number. They don't match, and nobody can fully explain why. And in 2025, a group of Hungarian researchers, Szigeti, Saputi, Barna, and Barnafoldi, revived Gödel's ghost. They showed that if the universe had a tiny, tiny rotation, far too small to have been spotted directly, it could nudge those two expansion measurements back into agreement. A whisper of a spin. Something like 2/millionths of a radian per million years. Almost nothing. But maybe not quite nothing. Other teams pushed back hard, running the Planck data and finding the rotation is consistent with exactly 0. So this is not settled. It is very much an open argument. But just imagine, for a moment, that it's true. That the whole universe, everything, the wall of light, the galaxies, you, this room, is turning, slowly, majestically, around some axis we can't see and may never find. And that somewhere in that turning is written the faint possibility that time itself does not only run in one direction. The universe might not be a thing sitting still in the dark. It might be a wheel, and we are too small, and our lives too short, to feel it move. Number 7. Universes a hair's breadth away. When people imagine other universes, they imagine distance. Other universes must be unthinkably far away, billions upon billions of light years out past the wall, separated from us by oceans of empty space. Far. Always far. There's a set of theories that says you've got the geometry completely wrong. The nearest other universe might not be far at all. It might be about a millimeter away. You just can't get there, because it's in a direction your body cannot move. This is brain world cosmology, and it comes out of string theory and its bigger cousin, M theory. The core idea is this. Our universe, all 3 dimensions of space that you live in, might be a membrane. A brain, for short. A vast sheet floating in a higher dimensional space that physicists call the bulk. Everything you have ever seen or touched is stuck to the surface of this sheet, the way a drawing is stuck to a piece of paper. And if our universe is one sheet, there's no reason there couldn't be others. Other brains. Other entire universes. Each a sheet of its own, floating in that same higher dimensional bulk, stacked near us like pages in a book. A page can be right up against the next page, almost touching, and the ink on one page has no way to reach the ink on the next. Not because it's far in any normal sense, because across the gap is a direction the ink simply cannot travel. That's where the other universe might be. Right there. A hair's breadth away, in a 4th spatial dimension you cannot point at, cannot walk into, cannot even really picture, close enough to whisper, forever sealed off. And then it gets bigger. In 2001, 4 physicists, Justin Corey, Bert Overett, Paul Steinhardt, and Neil Turok, took this picture and used it to explain the most important event in history, the Big Bang itself. Their theory is called the ekpyrotic universe, from a Greek word meaning out of fire, and the proposal is breathtaking. What if the Big Bang wasn't the beginning of everything from nothing? What if it was a collision? 2 of these brains, 2 universes, drifting toward each other across that tiny higher dimensional gap and slamming together. The unimaginable energy of that impact, spread across the entire sheet at once, would look exactly like a hot Big Bang. A whole universe of fire and light born from a crash. And in some versions, this happens again and again. The brains collide, bounce apart, drift back, and collide once more. A cyclic universe. Big bangs without end. Each one a fresh impact between worlds that never stop dancing toward each other. Now, is this proven? No. It's a serious, peer-reviewed alternative to the standard story of cosmic inflation, and it makes some predictions that differ from inflation, which is how we'll eventually test it. The extra dimensions it needs have never been directly detected. But the image stays with you, because we always assumed that if other universes existed, they were exiled to some impossible distance. This says the opposite. This says you might be pressed right up against another entire cosmos at this very moment. Another sheet, another set of stars, another version of the dark. Closer to you than the wall on the far side of your room. And the only thing keeping the two of you apart is a direction that, for your whole life, has been pointing somewhere you will never be able to look. Number 6. The swampland. So far, the trend has been universes multiplying. More space, maybe infinite. Other sheets a millimeter away. The story keeps saying, yes, there's more, there's always more. This one turns around and says something colder. Most universes are not allowed to exist at all. To get why that's so unsettling, you need the setup. String theory, our best candidate for a final theory that unites gravity with everything else, has an embarrassing feature. It doesn't predict one universe. When you work through the math, it allows a staggering number of possible universes, each with different physical constants, different particles, different forces, different rules entirely. We'll come back to just how many in a minute, because that number is its own item on this list. For now, here's the point. Physicists called that vast collection of possible, consistent-looking universes the landscape. And the comforting assumption was that almost anything you could write down, any reasonable-looking set of laws, would correspond to a real possible universe, somewhere in that landscape. Then, Qumran Vafa, a string theorist at Harvard, said, "Hold on, not so fast." Vafa proposed that out of all the universes that look mathematically consistent on paper, the overwhelming majority are secretly broken. They seem fine. You can write down their equations. But the moment you demand that they also contain gravity in a fully consistent way, they fall apart. They cannot actually exist. He gave the impossible ones a name: the swampland. The landscape is the small, dry, solid ground of universes that genuinely work. And surrounding it, vast and treacherous, is the swampland, full of universes that look like real ground, but will swallow you the moment you step on them. Things that look consistent, in his words, but ultimately are not. And here's where it stops being abstract and starts being personal. Because Vafa and his colleagues proposed a specific rule, the de Sitter swampland conjecture, that says universes with a stable, steady amount of dark energy, a constant positive energy baked into empty space, belong in the swampland. They're forbidden. You see the problem. Our universe appears to have exactly that. Dark energy, pushing everything apart at an accelerating rate, looking for all the world like a steady, constant feature of space. The very thing the conjecture says shouldn't be allowed. Read that again. The same string theory that generates a near infinite landscape of possible universes might, with this rule, be quietly declaring that the one we actually live in is impossible. A theory at war with itself, with us caught in the crossfire. Now, in fairness, this is one of the hottest fights in theoretical physics, and it is nowhere near resolved. Plenty of brilliant people argue that stable dark energy universes can be built in string theory just fine, and that Vafa's conjecture is wrong. The swampland might be smaller than he thinks. Our existence might be perfectly legal after all. But think about what's even on the table here. We've spent this whole video asking what's beyond the edge, picturing more and more out there. And this theory hands us a stranger possibility. That past the edge isn't a fullness, it's a fence. A boundary between the few universes that are permitted to be real and the endless, seductive crowd of ones that can never draw a single breath. And we are standing somewhere near that fence, not entirely sure which side we're on. Number 5. Physics changes across the sky. Here is the bedrock assumption underneath all of science. The laws of physics are the same everywhere. The same here as in the next galaxy. The same on the far side of the wall of light as in your kitchen. We call it the cosmological principle, and basically everything we believe rests on it. Take it away, and the whole structure wobbles. Now let me tell you about a number called the fine structure constant. It's one of the most important numbers in all of physics, written by the symbol alpha, and its value is about 1 over 137. What it controls is the strength of electromagnetism, which is to say, it controls how atoms hold together, how chemistry works, how light and matter talk to each other. If alpha were much different, you wouldn't have stable atoms. You wouldn't have stars that burn the way ours does. You wouldn't have chemistry. You wouldn't have you. And it's a constant. It's supposed to be the same everywhere and for all time. That's the whole idea of a constant. Then, a team led by an astrophysicist named John Webb, and to be clear, that's John Webb the scientist, not the James Webb Telescope, started doing something clever. They used distant quasars, blazingly bright cores of faraway galaxies, as cosmic flashlights. As that light travels billions of years to reach us, it passes through clouds of gas, and those clouds absorb very specific colors out of the beam, leaving a barcode of dark lines. And the exact spacing of that barcode depends on the value of the fine structure constant in that cloud, billions of years ago and billions of light years away. So they could measure alpha across enormous reaches of space and time. And what they found, starting in the late 2000s, made people genuinely uncomfortable. Alpha wasn't the same everywhere. When they looked in one direction in the sky, alpha seemed very slightly larger. When they looked in the opposite direction, it seemed very slightly smaller. Not random scatter. A pattern. A smooth gradient across the sky, pointing along a particular axis, like the universe had a built-in direction where the strength of electromagnetism gently shifted. They called it the dipole. And the statistical significance came out around 4.1 sigma, which translates to roughly a 1 in 15,000 chance of being a random fluke. Think about what that would mean if it's real. It would mean the laws of physics are not the same everywhere. It would mean that as you traveled far enough across the universe, the rules would slide. Just a little. And way out past the edge, beyond what we can see, alpha might drift so far that atoms as we know them couldn't form. Whole regions where chemistry breaks. Where the universe is built out of rules we don't have names for. Now, the honest part. This result has never been confirmed at higher significance, and a lot of physicists suspect it's a systematic error, something subtle in how the two telescopes were calibrated, rather than a real feature of the cosmos. Other, more precise measurements of single systems find no variation at all. So this is not a fact. This is a haunting maybe. But it's the kind of maybe that keeps the lights on late in a physics department. Because every one of us, every textbook, every equation, has quietly assumed that the rules out there are the rules in here. And a faint barcode in the light of dead galaxies whispered, for just a moment, what if they're not? The constants might not be constant. And if even one of them isn't, the universe past the edge could be a place where nothing we know would survive. Number 4, the closed universe crisis. Earlier, I told you the universe is flat, that every careful measurement says space has no overall curve, which is part of why we think it might be infinite. And that's the mainstream view, the comfortable view, the one in the textbooks. In 2020, 3 respected cosmologists looked very hard at the data and said quietly, "We're not so sure." And what they suggested would, in their own words, be a possible crisis for cosmology. Their names are Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk. And the data they were staring at came from the Planck satellite, our best, most detailed map of that ancient wall of light. Buried inside that map is a subtle signal. The way the cosmic microwave background gets gently distorted, lensed, by all the matter its light passed on the way to us, and the amount of lensing in the Planck data came out a little too high, more than the standard flat universe model predicts. So Di Valentino and her colleagues asked a simple question: what naturally produces extra lensing like this? And one clean answer is a closed universe. A universe with positive curvature. One that curves back on itself, like the surface of an enormous sphere. When they ran it, the Planck spectra preferred a closed universe at more than 99% confidence. Let me tell you what a closed universe actually means, because it's wild. In a closed universe, space is finite. It has a total size, and it has no edge, in the same way the surface of the Earth has no edge. You can walk forever and never fall off, because you just keep coming back around. In a closed cosmos, if you got in a ship and flew in a perfectly straight line, never turning, and you had infinite time, you would eventually arrive back exactly where you started, having gone straight the entire way. So in this picture, what's past the edge of the universe has the strangest answer yet. There is no past the edge. There's no edge to get past. Go far enough in any direction, and you just come home. The universe would be like a room with no walls that somehow still contains you completely. That alone would be mind-bending. But it's the second word in their paper's title that really lands: crisis. Because a closed universe doesn't just quietly slot in. It fights with everything else we've measured. It disagrees with our readings of how fast the universe expands. It disagrees with the patterns left by sound waves in the early cosmos. Take the closed universe seriously, and a whole set of measurements that used to roughly agree suddenly start contradicting each other, worse than before, which leaves us with a genuinely uncomfortable fork. Either the flatness we've always assumed is masking real contradictions in our model, or the lensing signal is a statistical fluke and a known systematic, and the universe is flat after all, and there's nothing to see here. Most cosmologists currently lean toward fluke. The closed universe paper is a minority position, and you should know that. But it's a minority position written by serious people, published in Nature Astronomy, based on the best dataset we have. It's not a crank theory. It's a crack in the foundation that we're all hoping is just a trick of the light. And until we know for sure, we're left with this dizzying possibility: that the universe isn't an endless plane stretching past every horizon, that it's closed, finite, curved, a cosmos shaped so that every direction out is also, secretly, a direction back. Number 3, the Great Isolation. Up to now, the edge has been a fixed thing, a wall, a horizon, a boundary that just sits out there. This one is different, and it's the one that genuinely unsettles me, because the edge in this story is moving. It's closing in, and it's taking the universe away from us, piece by piece, right now, as you watch this. The culprit is dark energy. We don't know what it is, but we know what it does. It pushes. It's a faint pressure built into empty space itself, and it's making the expansion of the universe accelerate. Things aren't just flying apart. They're flying apart faster and faster. And here's the consequence: almost nobody is told. Because the expansion is accelerating, there is a boundary around us called the cosmic event horizon. It sits about 16 billion light years away, and it works like the point of no return around a black hole, except inverted. Any galaxy beyond it is being carried away from us so fast by the stretching of space that light leaving it right now will never, ever reach us. We are sealed off from it forever, and galaxies are crossing that line all the time. As space accelerates, more and more of the distant universe is being swept past the horizon and out of our reach for good. Astronomers estimate that something like 94% of the galaxies we can currently see are already beyond it. We can still see their old light that left long ago, but we could never get there, and a signal we sent today would never arrive. They're like ships that have already sailed over the horizon. We see the light they sent yesterday. They are gone. So the reachable universe is shrinking. Every second, the cosmos we could, in principle, ever touch gets a little smaller, and the answer to what's past the edge becomes heartbreaking. Past the edge is almost everything. Almost the entire universe is already out there, on the far side of a line we can never cross, drifting further every moment. Now, run the clock forward. Way forward. About 100 billion years from now, the consequences are staggering. The Milky Way and Andromeda will have merged into one great galaxy. And every other galaxy, everyone, will have crossed the event horizon and vanished from view. The night sky of that era will contain our own galaxy, and beyond it, perfect, total, endless black. And here's the part that turns the loneliness into something darker. Imagine astronomers living in that far future, on some world in that lone galaxy. They look up. They see stars, their own galaxy, and nothing else. No other galaxies. No evidence of expansion, because there's nothing left to watch recede. No cosmic microwave background, stretched away to undetectable. They would have no way, none, to discover that the universe was ever bigger. They would conclude, reasonably, carefully, scientifically, that their single galaxy was the entire universe, sitting static in the dark, the way humans believed not so long ago. The truth will still be true. The universe will still be vast, still be full of galaxies, all of them just permanently out of sight. But the evidence will be gone. The edge will have closed over it like water over a stone. We are, it turns out, living in a privileged moment. Early enough that the sky is still full. Early enough to look out and see that we are not alone. That there's a whole cosmos out there. Future minds won't get that. They'll inherit a universe that lies to them by omission. So look up while you still can. The edge is closing, and everything it takes, it keeps. Number 2. The landscape of 10 to the 500th universes. I told you we'd come back to the number. Here it is. String theory, when you actually try to pin it down to describe our world, runs into the problem we touched earlier. It doesn't give you one universe. It gives you choices. The theory needs extra dimensions, curled up small, and the ways you can fold and shape those extra dimensions, and the fields you can thread through them, lead to different sets of physical laws, different particle masses, different forces, different values for constants, like the dark energy that's tearing the future apart. And when physicists counted, roughly, how many distinct ways you could do this, how many self-consistent universes the theory seems to permit, the number that came out was about 10 to the 500th. Let me try to make that real, because it's a number that defeats the imagination. 1,000,000 is a 1 with 6 zeros. 1,000,000,000, 9 zeros. The number of atoms in the entire observable universe is around 10 to the 80th. 10 to the 500th isn't a bit bigger than that. It's that number times itself, several times over. It is so far beyond the count of every atom in every galaxy we can see that the comparison stops meaning anything. It is, for all human purposes, a stand-in for more than you can ever grasp. Each one a possible universe, each with its own laws. Leonard Susskind, one of the founders of string theory, gave this its name, the landscape. A vast terrain of possible universes, 10 to the 500th valleys, each one a world with its own rules. And he paired it with an idea that's either the most profound or the most slippery thought in modern physics, depending on who you ask. The anthropic principle. Here's the puzzle it solves. Our universe looks absurdly fine-tuned. The clearest example is dark energy. The amount of it is small, but not zero, and its value sits at something like 1 part in 10 to the 120th of what the simplest theory predicts. If it were much bigger, the universe would have flown apart before a single galaxy could form. No stars, no planets, no us. The number looks impossibly, suspiciously perfect for life. For a long time, that perfection felt like it demanded an explanation. Why this value? Why so exactly right? The landscape gives a chilling, deflating answer. There is no why. There are 10 to the 500th universes, with every possible value of dark energy spread across them. In the overwhelming majority, the value is hostile, and nothing ever lives to wonder about it. We don't live in a fine-tuned universe because something tuned it. We live in one of the rare ones that allows observers, because those are the only ones with observers in them to look around. A dead universe has no astronomers to notice it's dead. So what's past the edge in this picture? Not one other cosmos, not a handful. A near infinite landscape of them, stretching off in the abstract space of possibility. Almost all of them sterile, dark, and silent. And our universe, with its stars and its chemistry and its strange habit of producing creatures that look up, is not the center of anything. It's a lottery ticket that happened to win. One bright valley in an endless range of mostly empty hills. It's humbling in a way that's hard to shake. We spent most of history believing we were the point. And the landscape says we might just be the place where the numbers, by sheer brute chance, across unthinkable odds, happen to come up in our favor. Number 1. An infinite universe means there's another you. We've gone to some strange places. Walls of ancient light, universes a millimeter away, a spinning cosmos, a closing horizon, a landscape of 10 to the 500th dead worlds. And for all of that, every one of those ideas needed some new physics, some unproven theory, some leap. This last one needs none of that. This last one follows from things we already believe, and it might be the strangest of all. Go back to item 9. Remember how we said the universe is flat, and that a flat universe is very likely infinite, endless, going on forever in every direction. Most cosmologists take that seriously. It's not exotic. It might just be true. Now follow the logic, slowly, because it leads somewhere that does not feel like it should be allowed. If space is truly infinite, then there is an infinite amount of matter in it, and matter can only arrange itself in so many ways. A region of space, the size of our observable universe, contains a finite number of particles, in a finite number of possible arrangements. A huge number, an absurd number, but finite. There are only so many ways to assemble a chunk of cosmos. So you have a finite number of possible arrangements, and an infinite amount of space to play them out in. And that combination has an inescapable conclusion. Every possible arrangement doesn't just happen once. It happens infinitely, many times. If you have infinite space and only finitely many ways to fill a given volume, the patterns have to repeat. They are forced to. Which means somewhere out there, far enough away, there is a region of space identical to this one. Same galaxies, same Earth, same room, same you. Reading this, right now. This isn't fringe. The cosmologist Max Tegmark at MIT laid it out carefully back in 2003 and called it the Level 1 multiverse. And he even worked out, roughly, how far you'd have to travel to find your nearest perfect copy. The number is so large it breaks normal notation. You don't write it as 10 to some power. You write it as 10 to the power of 10 to the power of 115, a tower of exponents. A distance so vast that the observable universe is less than a dust mote beside it. But the distance doesn't matter as much as the certainty. If space is infinite, the copy isn't a maybe, it's a must. There is another you, and not just one, infinitely many. There's a version of you who made the one different choice you still think about at night. A version who said yes instead of no. A version where the person you lost never left. A version reading these exact words in a room exactly like this one, with one tiny detail changed. And a version with nothing changed at all, identical down to the last atom, living a life that has so far matched yours perfectly, beat for beat, breath for breath, and you will never meet them. That's the ache of it. They're past the edge, far beyond the wall of light, far beyond the event horizon, separated from you by a distance you can't even properly name. Not hidden by some force or some wall. Just too far. The universe made copies of you and scattered them so far apart that none of you will ever know the others were real. So what's past the edge of the universe? After everything, here's the answer that stays with me. Past the edge is more of us. More of everything. Every life that could have been lived, being lived somewhere, by someone with your face. The universe, if it's infinite, isn't just big. It's a place where nothing is ever truly unique, and nothing is ever truly lost, because everything that can exist does, somewhere, endlessly. We started this whole journey staring at a wall of light, asking what's on the other side, and the most honest, most unsettling answer might be the gentlest one. On the other side is you, looking back this way, asking the very same question. And for one quiet moment, across an impossible distance, the two of you are wondering the exact same thing. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them.